So Argonne has its roots in the Manhattan Project. Imagine this bureaucratic problem. You have the top guy in your program, which is top secret. He needs a security clearance, and he's an enemy alien because we're at war with Italy. So figure that one out. Somehow, I guess General Groves got that taken care of. But to me, that is probably an accomplishment that rivals the invention of the first man-made self-sustained nuclear chain reaction. So anyway, but I'm not cynical. So December 2nd, 1942 was the culminating experiment. There was a series of experiments before then where the pile was assembled bit by bit and then measurements were taken and so forth. It's a standard approach to criticality for a new reactor design where you sneak up on it. There are some people who think, well, this is really a dangerous experiment because we didn't know what we were doing. Well, Enrico Fermi knew exactly what he was doing. He is still viewed as being the best neutron physicist to ever live because he was a master of experiment and he was a complete theoretical genius as well. And we may have had better experimentalists or better theoreticians in that field, but he's the one who had the whole package in spades. But this was a huge technological accomplishment. It's kind of like the discovery of fire because it's the word nuclear is an adjective that modifies two nouns. One of them is weapons and the other one is power or energy. There's a lot of problems in our society today with conflation of those two, and so a lot of people just kind of don't think very much of this accomplishment. But it was a stupendous accomplishment. And there were others who were trying and who failed, specifically the Germans, which of course was the relevant contest of the time. The Japanese also had a program, but the Germans were the farthest along. Argonne has never been involved in weapons design, but we did do the designs of at least the early plutonium and tritium production reactors. I would say there are three kinds of reactors. One is truly experimental reactors that are used for physics testing. In other words, the behavior of the chain reaction in the presence of various materials that one would build a reactor out of. And those are our zero power reactors. They don't need a cooling system. Then there are research reactors, which may be power reactors. They are not used for electricity generation, but they generate enough power that they must have a cooling system. And some of those reactors have been used to produce materials for nuclear weapons. So in fact, that's what the Pakistanis and the Indians did, and the North Koreans have done it, and that's how we did it. Commercial power reactors are designed and built and optimized to produce power for electricity, heat for electricity, and they are much more difficult to refuel, for example, than a research reactor. So it's harder to operate them in a way to produce plutonium for weapons, and it's also extremely uneconomical to do so. So commercial power reactors are definitely not the way to produce weapons material, and the United States has never done that. And I think some of the other countries use sort of a dual-use technology, like the British and the French used something called Magnox, and the Russians had some smaller versions of the Chernobyl reactor that produced both electricity and plutonium for weapons. But PWRs and BWRs, the reactors that are the most common power-producing reactors in the world, have never been used by anybody for producing weapons material. It's pretty much impossible to get to and use for a weapon. It's the wrong kind of plutonium, it's got too much other radioactivity in it, it's got the wrong plutonium isotopes. Nobody, if they wanted to build a plutonium bomb, would use a commercial reactor. It's much cheaper and easier to use a dedicated reactor like we did at Hanford and at Savannah River. Anyway, we built EBR-2 in Idaho. It was a full-scale power plant, not commercial scale, but it had a steam plant, generated electricity, ran for 30 years. It's a sodium-cooled fast reactor. It demonstrated all kinds of things, inherent safety. It demonstrated nuclear fuel recycling in-house and proliferation resistance and fuel performance. So
what's the core size?
It was 20 megawatts electric, 60 megawatts thermal.
But what's the physical size?
Bread box, about like this.
Bread box.
Yeah. Somehow, and maybe somebody here can explain this to me, nuclear technology ended up on the right side of the political spectrum. And so people on the left were hostile to nuclear technology. I personally believe it's because of a false association with nuclear weapons. And so essentially you have the one group that would be in favor of a government program to develop this technology, doesn't like the technology. That would be the Democrats. I'm grossly generalizing. On the other side, the Republicans, who maybe would tend to favor this technology more, aren't really, they don't want to have a lot of big government programs. It's the classic government battle that we always have. And our technology has kind of gotten wrapped up in that. And this was shut down in 1994. The charge was led by then Senator John Kerry. And so he and President Clinton decided this was a bad idea, and they terminated the program. There's a lot of nuclear going on here. We haven't built any reactors. We haven't operated any reactors.
Oh, it's just safety analysis or what?
Safety analysis, fuel cycle analysis. We do a lot of work. For example, we want to know, well, what if we recycle nuclear fuel once in light water reactors? So what's the outcome in terms of what a repository needs to be like, for example, geologic repository for spent fuel. And there's a whole range of fuel cycles, including thorium, that we've studied, and what comes out the other end after X decades of operation, let's say.
But do we get to see an operating reactor today?
Absolutely not. We don't have any.
Oh.
Sorry. Nope.
That was the decision of Clinton?
No, it's a cumulative decision, not just Clinton.
So let's say the guys that run this place decide we really want to get in and build a brand new reactor. We want to do something a little different. We want to build a thorium reactor. So if you guys had the will on this campus and said we want to do this, what's the process to make that happen, and who would oppose, stop, or assist you in that?
Well, it costs money. So who's going to pay? So we need a private partner, or we need a congressional appropriation.
Okay.
Those are the key stumbling blocks.
So if you guys decided you wanted to build a new reactor, and this didn't come down from Department of Energy, and then somebody, your senator, your federal senator, goes out, gets a bill, gets you funded, and you want to do a reactor that you guys have come up with on your own, are there any political problems with that within the DOE?
I doubt it for that. I don't really know. I don't work with DOE myself very much, and I certainly don't work at the political level.
Yeah.
But I have heard a very high level DOE official say, "If you get me the money, we'll do your project."
How much of the lab funding is private now?
We get some funding from private. I don't know how much it is. We get some funding from foreign countries. For example, we're doing some reactor safety experiments for an international consortium. That's molten core concrete interaction experiments. And there's one that we're doing right now funded by France, the government of France. The South Koreans have an advanced reactor design project that we're helping them with. We have a contract with them. So there is some international collaboration going.
I mean, there's still the reactor out by the light source, by like the guest house.
That's EBWR. CP5 is now Greenfield.
Oh, okay.
So
that's just
when you head up the hill to building 316, the field to your right is where CP5 was.
So what's the still standing reactor building out there?
That's EBWR, experimental boiling water reactor.
So that just got mothballed 40 years ago probably, huh?
Yep. So I guess.
Why is it still? How come they didn't dismantle that?
I don't know.
Why do they even dismantle reactors? Because it's like I always assumed that was a fine end state for a reactor is just to have an abandoned building?
That's a very good question, and I don't understand why you have to return a reactor site to greenfield when you don't need to do that for any other industrial facility that you stop using.
Do you see how much work they did to the NASA reactor in Ohio? God, it blew. Man, it'll blow your mind if you didn't see it, the amount of work it took.
Oh yeah, it's a huge amount of money to reduce essentially a negligible risk. Yeah, I could come up with all kinds of political theories, but I'm certainly not going to do so on camera.
I think it's the energy solutions full.
May I ask what happened to your reactor that was to power rockets?
I don't think we built a rocket test reactor. We may have had a critical reactor. Maybe one of these fast criticals was used to study the physics of a design that would have been for a rocket reactor. So that would have been in Idaho. In our laboratory in Idaho. Now, the ones in Idaho, we designed, built, and operated 14 reactors in Idaho, and we shut them all down. And then the reactor sites, there was a new laboratory started up in 2005, Idaho National Laboratory, which basically took our experimental facilities at Argonne West. So they are the custodian of the sites where these reactors used to operate.
But why was the rocket-powered reactor dropped?
I don't know.
Does anybody?
You're talking about Nerva or Kiwi or BB
I'm not familiar which is the name, but clearly we don't have them now, and they worked on it. So it would be nice to know.
The nuclear reactor for the rocket propulsion.
Right.
It all died at the end of the Apollo program when Nixon killed the Apollo program, because that's what happened to the SNAP program for the little trash can reactors for auxiliary power for space systems, and the Nerva rocket systems for space propulsion. This was all part of the follow-on, the Apollo Applied project. So yeah, it all got killed by Nixon. So early in the administration.
Many of you have probably seen one version or another of this curve. There are a couple of reasons for fast reactors. One is better safety. Not that our current, nothing I say here, by the way, should be taken as a criticism of our current reactors. They're perfectly adequate. They're safe enough. They don't present any risk. They present a far lower risk to society than most of the other power production means that we have. Having said that, fast reactors have some advantages. And one of them is improved safety. Another one is resource extension, where we can use basically 100% of the energy in the uranium ore instead of just 1%. And another one is waste reduction. And this plot here shows how waste reduction works in a fast reactor. Now, I'm going to have to hit you with some nuclear physics here. In a fast neutron spectrum, where the neutrons don't slow down, elements that don't fission in a regular thermal reactor will fission. Those elements are plutonium-240, 242, curium, americium, californium, and those are the bad guys in the repository. Those are the elements that make you have to design a repository to last 300,000 years or whatever the number is. So if you can convert those to short half-life materials, then you just made your repository design problem a lot simpler. So these are two curves. This is relative radiotoxicity. The dashed line is uranium ore in the ground. So it's radiotoxic. Now we have no national program to dig up all that stuff and sequester it to protect our society from the health effects of uranium ore. So I think we could all agree that if we can get our spent nuclear fuel into a state that is no more radiotoxic than that uranium ore, then we have satisfied our obligation to society to protect them from health effects. This is a log-log plot, so that's 10 years after discharge, a million years after discharge. This is the ore toxicity. So 10 years after discharge, the radiotoxicity of spent nuclear fuel or used nuclear fuel is about 1,000 times uranium ore. It sounds like a lot, but really it's not that, a factor of 1,000, considering that uranium ore is not really considered a problem, looks entirely manageable. But nonetheless, what are the constituents of that? At the beginning, a lot of it's fission products, and the fission products of concern in this case, are mostly strontium and cesium. They have 30-year half-lives, and that's what they're talking about in Japan right now. That's the residue from the Fukushima releases. The biggest one is iodine-131. That has a half-life of 8 days. So by the time we take our fuel out of a reactor, there isn't any radioiodine-131 in it. So these are the fission products, and you can see the fission products drop off with this 30-year half-life. After a few hundred years, they drop off to less than the radiotoxicity of uranium ore. This stuff is the plutonium, americium, curium, californium, stuff like that. This stuff fissions in a fast neutron spectrum and becomes this stuff. So, and you can only do this with any measurable effect in a fast neutron spectrum. Any thermal neutron spectrum will not do that. So we propose that we build a fleet of fast reactors, and we fuel them with spent fuel from our current light water reactor fleet, and we fission all that stuff, and this is what we're left with. And you can fit, I've seen plots, if you, depending on how efficient your recycling is, your segregation of radionuclides, you can fit the spent nuclear fuel or the waste from spent nuclear fuel 200 times more energy in the Yucca Mountain repository, for example, than you can if you just put the spent fuel in. So this is a tremendous way of making this problem a lot more tractable. The time scales are hugely different. So that's really the salient feature here. Now, how do we do this? And the system that we devised to do this is called the Integral Fast Reactor. It has actually a similarity to the molten salt reactor in that it's on-site recycling, although it's not in the reactor, the primary system. So it doesn't involve shipping fuel around, use spent fuel and all that. You actually don't want to do that. You want to recycle kind of promptly. And the system we have devised is called pyroprocessing, which is electrometallurgical. It doesn't involve aqueous chemical systems, which tend to be much more complex, much more expensive to build, very difficult to maintain because you've got radionuclides and concentrated nitric acid, and it's well, the French do it quite well, but it's very challenging. Pyroprocessing is a little batch system, so it doesn't involve piping systems, so it's a bit like a computer in that if you have a component failure in this recycling system, then you can swap in a new one and take the old one out and throw it away or whatever. So in terms of operations, it's simpler. It's probably about 10 times smaller in physical scale, and in terms of materials, so it's, I think, costs about 1/7 as much as a similar sized aqueous reprocessing plant. But the main thing is, our system never ever separates plutonium from uranium. And it never completely gets rid of the fission products. So what the system the French use for recycling produces plutonium dioxide, which is then mixed with uranium dioxide to make MOX for reactors, and it works fine. We call that a clean fuel, dirty waste system. So they still have to deal in the repository with the americium, the curium, and all that stuff, not the plutonium. Ours is a dirty fuel, clean waste system in that what comes out at the end is fission products plus maybe some trace amounts of the heavy stuff. So the bad stuff all goes back in the reactor, including some of the fission products, which make this material self-protecting. So if you were someone who wanted to steal material to make a bomb, this is the very last material you would consider. First off, it would have to be a suicide operation to do it. Second off, it's got all these neutron emitters and heat emitters in it that would make it impossible to put an explosive lens around the plutonium bomb, an HE explosion lens, which is part of the bomb design. that would just melt. So it's as secure from a proliferation point of view as you can get. So a pressurized water reactor is 3 meters in diameter and 3 meters tall. That's where the uranium is, okay? The same size for 1,000 megawatts. A 1,000 megawatt fast reactor is about 1 meter across and 1 meter tall. How do we do that? We don't use water as a coolant. We use liquid metal, in our case sodium, and the thermal conductivity of liquid metal sodium is 100 times that of water. So it's an enormously better coolant. You can also use, by the way, you can use a steel clad instead of a zircaloy clad, and zircaloy is what reacted with the water at Fukushima to release hydrogen, which then had a chemical explosion outside of the reactors. This reactor is inherently safe specifically because it uses liquid metal sodium as a coolant and because it has a metal fuel, not a ceramic fuel. A metal fuel is very nice because you can cast it. You can use injection casting to fabricate fuel elements in our recycling plant. Our plant, this is a mock-up of the recycling plant we built at Argonne West, and spent fuel comes in and fresh fuel goes out, and it's attached to the reactor. Oxidation of sodium is about 4 times less exothermic than oxidation of, let's say, firewood. So firewood is a self-sustaining chain reaction where heat takes the place of the neutrons sort of in sustaining it. There is so little heat produced in sodium oxidation that it can't sustain a very fast chain reaction, a combustion chain reaction, except in water. But in air, it sort of fizzles and hisses and stuff like that. The Japanese had a sodium leak at one of their reactors, and it just sort of, it makes a mess, but it doesn't really do any damage like a fire would. So to call it a fire, it is combustion, but to call it a fire is sort of an exaggeration. So the engineering challenge is to keep the water away from the sodium, which we did at EBR2 for 30 years. It really was not a problem.
What are the chances a flood would affect a reactor like that?
Well, you wouldn't put it in a place where it would be flooded, so just like you wouldn't put your electric switchgear.
Japan would never get one.
Well, they could, if they'd had one of these 100 meters up the hill, they might have had no accident at all because these reactors are passively safe. It's a low pressure system, just like the molten salt reactor, so leak is not really that big of an issue. If there's a leak, it's not getting shoved out at 2,000 pounds per square inch, and that means you can afford to have a relatively thin vessel. A commercial PWR reactor vessel is about 8 inches thick because it's got to hold well over 2,000 pounds per square inch pressure. The molten salt reactor and the IFR operate at basically bicycle tire pressure. So you can have a 1 inch thick vessel, roughly speaking, which makes it's a lot cheaper to make. So you can make a really big one and put a whole lot of sodium in there. And now you have this massive heat sink, which can absorb heat from this reactor if you use electric power. So if we could design a seismically qualified one, if we had done so and we had put it at Fukushima, they would have had no accident.
Did the sodium act as your sole passive decay heat removal?
Yes.
So it's just like a big pool.
It's a very nice material for natural circulation.
So you didn't need to draw it off or have like an external heat exchanger to run fast?
Well, ultimately you have to remove the heat from the reactor system.
Like in a scram situation or if it shut down, it would just absorb. Right. Would it get into a pulsation type situation?
No. In fact, we've done exactly that. We understand very well the safety characteristics of the Integral Fast Reactor, and I've got 3 minutes, 5 minutes. So we, after doing a lot of analysis, obviously, we conducted some tests at EBR2 in Idaho. We took EBR2 to 100% power, and we gagged the safety system so the emergency control rods would not go in if they were told to. And then we turned off the main coolant pumps. So what happened is what we expected, namely the coolant going through the core slows down, so it picks up more heat per unit mass as it goes through, so it comes out the top hotter, and the core tends to expand thermally a little bit as it heats up, and now more neutrons leak out and don't contribute to the chain reaction. Now in any reactor, it's a very fine balance. And so any perturbation can make a very big difference. In this case, a little core expansion reduces the chain reaction to the point where it pretty much stops. So what you're left with is a system that is critical still, but it's at not producing any power to speak of from the chain reaction, only the decay heat. And now there's natural circulation going on inside this big vessel, so you don't have to put the coolant in, it's already there. And it's absorbing heat. Now ultimately, you need to remove that heat. But since it's a big vessel, it has a big surface area, and you could design it so that natural air circulation on the outside of this, we can make this thin vessel, we can afford 2 of them.
Yeah.
So we put one outside the inner one, and so if the inner one leaks, we still don't have a leak. So that's another nice feature. But a commercial reactor, we would design it with a natural circulation, natural air heat removal that would occur. And so you would actually never ever need to take operator action. That would be the design goal.
Sure.
I don't know if Pandora's Promise has changed public opinion. I think it has motivated some people who had been either skeptical of nuclear or were anti-nuclear to rethink that, and the combination with climate change. That's, I think, the big difference today about public perception of nuclear is before, nuclear was another way to generate electricity, and it had all these supposed downsides, which were factually true, but in terms of real impact were just sort of made up. Now there is a definitive reason to pursue nuclear energy, and that's climate change.